In the round table on AWS, Azure, and GCP. We got to this slide, so I'm going to continue from this point. This slide is about messaging and workflows, and all three clouds offer solutions in this area, and I'm going to explain how they're different and how they're similar. So in Azure, they have something called queues, and in AWS, they have something called SQS. And in GCP, they have something called Cloud Task Queues. These three are all very similar in function. Pretty much they're a first in, first out queuing system, which basically means you put in a message and it comes out in the order it was placed in. However, there are two modes typically in these three. One mode is enforced first in, first out, and the other one is kind of best attempt at first in, first out. So the default is usually the best attempt version, whereby the technology tries to ensure that the first message in is the first one out, but it doesn't guarantee it. And then there's usually like a flag that you can set or a switch that you can turn on that makes it so that it's guaranteed first in, first out messages. And this is very simple queues whereby a simple message is placed on the queue and a simple message is read from the queue. So there's a publisher and a consumer of a message. And all three of these are very similar. Now, other options in the various clouds are more complex. So for example, Azure Service Bus can be very complex. Can involve a lot of connectivity between different services and a lot of different types of event handling. So it can handle different types of events coming in from different parts of Azure, and it can publish to different parts of Azure as well. So it can be quite complex. The most similar thing to this in AWS really is SQS plus SNS. Now, SQS is the simple queuing system we already talked about. SNS is the notification system, which basically originally just notified things like email and text messages and things like that. But SNS has become really quite complex nowadays, and it can notify things like Teams and Slack. It can also notify other parts of the AWS architecture, so it's become a little bit more complex. The closest that GCP has in this space is using Kafka and using pub/sub, which is publisher and subscriber. And this basically means that multiple subscribers can consume the same message. And so Service Bus is like that too, and SNS is a bit like that too, that there can be multiple subscribers to the same message. So that's kind of the difference here. Event Grid is more about processing status changes and is very much like AWS Event Bridge. So in Azure, it's Event Grid, and AWS, it's Event Bridge. AWS also has serverless steps, which is workflow, which is kind of in this space too. When some status changes, it calls a function, or in AWS, when the status changes, it calls a Lambda function. And typically that's really quite simple workflow, simple status changes. And again, GCP implements this using Kafka. Kafka, by the way, is a pretty complex system. It can be used in any of these clouds. So Kafka allows really simple queues, but it also allows pretty complex queues. And there's different modes that you can use Kafka in. You can use Kafka kind of on-premise kind of Kafka. You can use managed Kafka, and you can use Confluent Kafka in the cloud. So depending on what kind of management you want to do, if you want to manage the underlying infrastructure, if you want more control, you might use the kind of on-premise or the managed Kafka. If you literally want AWS or Azure to take care of Kafka, or GCP take care of Kafka completely, you might want to just use Confluent Kafka. And literally then all you have to do is configure the messages and configure who's allowed to subscribe to those messages and who's allowed to publish to those messages. and what the sort of workflow is around that. So other options in this space are more complex. So logic apps in Azure, they basically handle if-then situations and repeating loops of calling a function in different scenarios and so on. And so you've got Azure Logic Apps. They coordinate with Azure functions according to which state the state machine is in, pretty much. So if a piece of data comes in one state and then moves to another state, there's a particular function that gets called in that scenario, for example. And the state machine can get quite complicated and complex. And it's similar to AWS Steps that calls Lambda workflow functions, and has a similar kind of state machine idea going on there. It used to be SWF in AWS. It used to be a simple workflow, but now it's AWS Steps with Lambdas, and it's all serverless in that case. Azure Notification Hub is a little bit like AWS SNS, which provides messaging, so messaging via emails or via text messages, and now to Slack and Teams and things like that. So Azure Notification Hub is very similar to SNS in that respect. And then AWS also has this SES, which is a little bit like SendGrid. Now SendGrid can be used on any of these platforms, but Azure has it kind of built into its whole processes. But it's basically, SES can be anything from simple email to really quite complex SMTP type services, and SendGrid can be a layer on top of that, giving you, a lot of complexity about your grouping of emails and the scheduling of emails, and the workflow really of when emails are being sent out and so on. So that's another part of this space. For this slide, I wanted to give you an idea of the kind of technical architectures you might have in Azure and in AWS. So on the left-hand side, you've got Azure, and on the right-hand side, you've got AWS. And you can see there's a lot of similarity here. This is a typical architecture you might have in either one of those clouds. So on the left-hand side, you have a virtual network, and on the right-hand side, you have a virtual private cloud. They're pretty similar in concept. There's differences, but they're pretty similar in concept. What's exposed outside of that virtual private cloud or virtual network is either a public IP in Azure or an elastic IP in AWS, which is basically the IP address of your system to the world out there on the internet. Inside of that, there's a load balancer typically in front of your front end virtual machines, and that load balancer in Azure would be called the Azure load balancer, and in AWS it would be called the Elastic load balancer. In this case, the load balancer is publicly accessible via the IP address we talked about before, and it shares traffic between the internal virtual machines. In this case, there are two in each case. It will share out, typically it will do a load balancing 50-50 on two virtual machines, but depends on how it's configured, but that's pretty typical. So those virtual machines are inside a subnet in both cases. Subnets are pretty similar in concept in both clouds. The way it's determined whether another virtual machine is added to that mix, if the load goes up, like if the memory goes over 80% on these virtual machines, things like that. In Azure, it's called a scale set, and in AWS, it's called an auto scaling group, but it's pretty similar. You basically put in some criteria and you say, for example, if virtual machine memory goes over 80%, then add another virtual machine, spin up another virtual machine to take a third of the load, kind of thing. And then it will scale back down again if the memory goes under, say, 40% or something like that. Within this subnet, the access controls within that subnet will be via a firewall, which is called a network security group in Azure, and a security group in AWS. That will determine which ports are open. Now, typically, these are going to be web servers in this subnet here. So, port 80 might be open, or port 443 for secure SSL, TLS access. So that's the first subnet. Now, that would be a more public subnet. Now, when you're in the old days, you would talk about a DMZ, a demilitarized zone, which would be a second subnet. And in this case, the second subnet might contain things like the middleware or the back end of the application. And again, that would normally go through a load balancer. But this time it's an internal load balancer, only accessible from those two virtual machines in the main subnet. And this subnet might include a couple of virtual machines. It might include databases and so on. And again, you have the two virtual machines by default. It could be scaled up using scale set or availability set and so on. And again, the security group at that level, this time it's going to allow connections on a different port typically. Like if it's a database, it might use the SQL Server database port and things like that. And then at the back end, you've got the storage. Typically, storage is going to be something like blob storage. So in Azure, you'd have Azure blobs. In AWS, you'd have S3, or the other type of storage you might have is like file storage. So in Azure storage, that would be files, and in AWS, it would be either EFS, which is Elastic File System, or you'd have EBS volumes, which are like hard disks in the cloud. And they would be accessible there. So that's just kind of a comparison of what the architectures look like in the different clouds, the two different clouds. One other point is that two virtual machines behind a load balancer, typically you'd want to put those in a spread placement group in AWS, which basically means that one virtual machine is on a different stack to the other virtual machine. So for example, it might be on a different rack, it might even be in a different location, just so that if one virtual machine goes down, the other virtual machine stays up, so that for disaster recovery and business continuity purposes and so on. So in AWS, that's called a spread placement group, and in Azure, it's called an availability set, and it's for availability to make sure that if one goes down, the other one will still be available. If they were both on the same stack in the same data center, there'd be a risk that both would go down together if there was a power outage, or if the building was hit by a meteor or something like that. So if they're both at different locations, different data centers, or at least on a different stack, there's less chance of them both going down at the same time. So that's what a spread placement group is in AWS, and in availability set in Azure. So a cluster placement group is almost the opposite of that. It's saying, I want these two virtual machines to be close in proximity. I want them to be on the same stack. And the reason you might do that is because you want fast access from one to the other. You want low latency. You want the network calls from one to the other to be very fast. So in this case, it might be from subnet 1 to subnet 2. You might want the virtual machine at the top to have fast access to the virtual machine at the bottom subnet. Because when the front end is calling the middle tier, you want that to be a fast interaction. You want the latency to be low. So that would be a case where you might use a proximity placement group in Azure or a cluster placement group in AWS. We talked about auto scaling groups, basically allowing a virtual machine to be added to the mix if the load goes up, and then to go back down if the load goes down. Normally that's managed by a load balancer and the rules attached to the load balancer. So we talked about that, and we talked about storage. So that's the end of this slide. Let's go on to the next one. We talked about the architecture of a typical infrastructure currently. Now we're talking about here a serverless architecture. So this is where the actual servers are managed by the cloud provider, either AWS or Azure. So typically in a serverless architecture, you're going to be using Azure functions in Azure, and you're going to use Lambdas in AWS typically. So this is typically how it might be set up. You might have at the front, you might have the front door, which basically is kind of the routing for accessing your system, and Route 53 in AWS is similar to front door in that respect, giving access to your APIs in this case, and your functions. And then within that, you may have what we call microservices. So there might be a cart microservice, an orders microservice, and an inventory microservice. Each one of those representing, an API endpoint, and you can have a get, a put, a post, a delete to each one of those. So there'd be the cart microservice. You could do a get to find out all the cart items, and you could do a post to add an item to the cart, and a delete to delete something from the cart, that kind of thing. So this is typically an API management system would allow you to do to make changes to that endpoint using get, put, post, delete. And there'd be API management or API manager in AWS would have some kind of security around it. You have to authenticate to prove who you are, and then there would be authorization to say, okay, now that I know who you are, now that I've seen that you've got that password, or you know something, you've done some sort of authentication, now what have you got access to? What's the authorization? And one person might have access to the cart but not the orders, and another person might have access to the inventory but not the cart, and that kind of thing. So API management takes care of that, or API manager in AWS. Now behind the scenes, these functions or lambdas are using services within AWS or within Azure. And these are the serverless options. So event hubs, storage blobs, notification hubs within Azure, and in AWS, SQS, which is that queuing mechanism we talked about earlier, S3, which is the equivalent of blobs, and SNS, which is the notification system, the message system we talked about earlier. So going to the left-hand side, as we said, Azure functions are very similar to AWS Lambdas. They're very small pieces of functionality, and typically they're used to implement like a microservice, one microservice typically. An Azure App Service is more like an app that can either run a website. Normally it has a front end that's accessible via the web. Can either run the website, or it can run a web app, which may be like a batch process, a background process, that kind of thing. Or it can also deploy APIs, which is basically like microservices, or containers that run a piece of functionality, which a container in this case you can think of as very similar to a function or a lambda, but the container kind of contains all the operating system's parts that it needs and so on. But again, a container can be used to implement a microservice. So again, all of this is kind of serverless. There's also GCP offers artifact registry, which is kind of like a way of registering which functions and which microservices are available. It's a little bit like these kind of architectures. Azure has Container Instance Service, which can be used to manage containers, which is very similar to AWS Fargate, a serverless container management system. So they're kind of similar. But Kubernetes is the up and coming, the kind of sexy way to manage your microservices, if you like. So Azure has Kubernetes service, AWS has EKS, which is Elastic Kubernetes Service, and there's also a GCP one, which I forget the name of. The Azure Kubernetes Service, as far as I know, is still a little bit more infrastructure based than EKS. The AWS EKS option is a kind of serverless option for managing your Kubernetes. You can also do a non-serverless version of Kubernetes in AWS. You can host your own Kubernetes on your own virtual machine and manage the infrastructure if you want to, but why bother when you've got EKS that will do all that for you, and it'll scale up for you automatically, and it'll do a lot of management for you automatically. If a container goes down, it will bring it back up and do some proxying and all that kind of stuff. So EKS, I think, is the most advanced in this area in the Kubernetes window. That gives you an idea of how serverless is implemented on the different clouds. I want you to have an idea of how hybrid solutions are managed in the different clouds. This one is AWS. Hybrid solutions are partly on-site and partly in the cloud, so partly on-premise and partly in the cloud. Direct Connect is AWS's main way of handling this situation. So on the right-hand side of this picture, you can see that the customer's network is on the right-hand side. So this is like the customer's data center, if you like. And the customer would put a firewall, a router, on this end, and it would have access to kind of like a pipeline called Direct Connect, which the pipeline is normally hosted by someone like AT&T or Comcast or a big service provider in their own colo, in their own data center, in their location. And it has to be provisioned, so it can take a couple of days, a couple of weeks, sometimes even months, I believe, to put this cable in place, because it's literally a line, a cable that goes from the customer's on-site premise, on-premise, to the data center owned by AT&T or Comcast or whoever it is. And so inside AT&T's colo or Comcast colo or whoever the service provider is, their colo location, it's called an AWS Direct Connect location. Inside there's kind of a right-hand side and a left-hand side. So the right-hand side is the connection to the customer, the client, and then on the left-hand side is the connection to the AWS. And AWS has these kind of very close relationships with these ISPs, these major ISPs, and gives them direct access to AWS on the left-hand side using an AWS Direct Connect endpoint. And this has kind of an internal and an external endpoint that it can access. So one is a private virtual interface and one is a public virtual interface. So the private virtual interface is used to access via a virtual private gateway to access the actual VPCs owned by the customer, the virtual subnets, the virtual networks that are owned by the customer. So there can be all kinds of stuff inside those subnets. There can be EC2 instances, there can be load balancers, databases, what have you. And then on the external side, so the public virtual interface, it uses that to access blobs owned by the customer like S3, Glacier, that kind of thing. Anything that's external. So DynamoDB has an external virtual interface, public virtual interface, and so on. So this is how like the ISP accesses the AWS side of things for that customer. So this is basically a two-way thing, so that the AWS architecture can access the customer and the customer can access AWS. But it's all according to the rules on the firewall on the customer side, of course. Okay, so that's AWS's answer to hybrid solutions, or one of the answers, I should say, to hybrid solutions. This is the Azure solution to hybrid solutions. That's kind of the equivalent to Direct Connect AWS. So it's called Azure Express Route, and it's actually right to left instead of left to right in this case. But the customer's network, as you can see, is on the left, it accesses the partner edge, which you can think of as AT&T or an ISP connection. And then it connects via the Microsoft Edge to the Microsoft network, including the the Azure network of this customer. So it's very similar. It's just in this diagram, it's right to left instead of left to right, but basically it's very similar. And again, there are public parts and private parts to what they can access each way, but very similar. So for some customers, it's really, really crucial that their direct connect link works at all times. And because of that, they might have redundancy requirements. So for example, they might have two direct connect connections in case one of the direct connect connections goes down. So this is on the right hand side here. This is in AWS. The customer would have a data center connection, as we said before, a router firewall connection on the right hand side, but in two different places, maybe in two different data centers, and would connect via maybe a different direct connect partner. So you might have one connection via AWS with AT&T and another one via AWS with Comcast, for example. You might have two different ISPs just to ensure that you have complete redundancy in the whole system. And again, AWS or Comcast would have a direct connect into the AWS virtual private gateway. So this is basically just a way to do a redundant backup option for direct connect, just in case one goes down. So this is the redundancy option for Azure ExpressRoute. Pretty similar in a way, but you basically have two ExpressRoute circuits from the partner edge to Microsoft Edge. Now this could be like AT&T having two separate ExpressRoute circuits, or it could actually be two separate partners, like in the previous slide where you had AT&T and Comcast, for example, both having an ExpressRoute circuit. So very similar. One redundancy option for Direct Connect in AWS is to have a VPN backup. So basically, Direct Connect usually does not go over the internet at all. The traffic is direct to AWS from the customer site. But as a backup option, in case the Direct Connect goes down, the client might decide it's too expensive to have two Direct Connect connections because they're very expensive. They're also very slow to set up. So rather than connect via a separate Direct Connect redundancy option, they could set up a VPN, which does go over the internet, but only when the other one is down. So only when the Direct Connect option isn't there, they might use the VPN. So in this case, they'd have a VPN gateway on site, which connects via the internet directly into the VPC on the AWS side. So that's a typical redundancy option for Direct Connect in AWS. Here is a typical redundancy option for ExpressRoute, where you don't have two ExpressRoute circuits. Instead, you have a VPN gateway and a VPN going directly into the AWS environment. So very similar really to the Direct Connect VPN backup. It's like Direct Connect with the AWS, ExpressRoute does not go over the public internet. Because it travels over a private connection, there's more reliability, faster speeds, lower latencies, higher security than typical internet connections. So that's both for ExpressRoute and for Direct Connect. So it's often used for privacy, for security reasons, but often used for faster speeds also. And there's a link there to the benefits and disadvantages. So there are other AWS connection options. The virtual gateway is VGW, the direct connect gateway is DGW, and the transit gateway is TGW. So there are options, and these are the benefits and disadvantages of each one. Some of them are globally available, some are not. Transitive routing is the big benefit of the transit gateway, which basically means just about any network can connect to any network. So It's not just one network to one other network, and so on. But there are lots of options there. You know, there are other options for on-premise hybrid type environments. In AWS, they have the option of outposts, which is basically it looks like you have AWS on-premise. It's really managed infrastructure from AWS, but it's placed on your on-premise data center or what have you. So outpost racks can be pre-configured with, you know, EC2 instances and EBS storage volumes and things like that. And they're kind of managed by AWS, but they're actually on your on-site. So you kind of get the benefit of cloud, but you have it on premise where you have more control over security and so on. A lot of people are worried about going into the cloud because of security reasons, and they feel that they have more control if their data is on premise, and so on. However, that is really an old-fashioned view, in my opinion. Nowadays, the cloud is probably more secure than anything you've got on premise. But those people that are worried about that, they like using outposts so that they can control some aspects like of security and so on, and also data location for compliance reasons and so on. So Outposts is the AWS solution to that. Azure Stack is pretty much the same for Azure, where you can basically have an Azure Stack on premise with you know, virtual machines kind of managed by Azure and so on. And Google Anthos is Google's response to this, mainly using VMware virtual machines and so on, but they're managed by Google GCP. This is just to show you really the maturity of these three options. AWS is way out in front pretty much. It provides not just VM instances, so not just EC2 instances, virtual machines, but also things like containers. Some of the serverless options are available. Some of the storage options are available, like S3 can be on-premise. Some of the database options can be on-premise, and some of the analytics like EMR and Hadoop and Apache Spark and so on are available. So AWS is way out in front. The only thing that really isn't available there is things like Lambda functions and Fargate. You can do things like Kubernetes on premise, even though that's not listed here, but you can do that with AWS. Now, Azure is kind of the next best in this area, but it doesn't provide the databases and analytics side of things on premise, because it already has SQL Server on premise and so on. You don't really need to use on premise Azure stacks for that kind of thing. So Google is behind on a lot of this stuff, and it's really just using VMware on premise for this kind of area. And to run your apps anywhere, and Azure Application Services is probably the most ahead in this area. Azure Arc is kind of the idea of running your applications no matter where they are, whether they're on Kubernetes, whether they're a container, or whether they're an app service, you know, whatever they are, functions, event grid, APIs, whatever, you can run it anywhere using Azure Arc to manage them, whether they're on premise or on the cloud. You can easily kind of, it's almost like you can cut and paste an application into a different environment, or copy and paste it into a different environment. It's pretty easy to do that. So AWS has a similar thing called AWS Anywhere. However, Azure seems to be way out ahead on this one, pretty much because Microsoft are used to managing apps, you know, on premise as well as in the cloud. So I think they're a little bit ahead, or quite a lot ahead on this area. So we talked earlier about AWS Steps and Azure Logic Apps. This is just to show you kind of what the state machine diagrams kind of look like, a simple one here. Particular states happen, and when a particular state happens, a particular function gets called In this case, the create order number function gets called, and then depending on a kind of if-then statement towards the bottom there, it either sends order information out to the customer or it gives some kind of delay and response in this case. But this is pretty much how the state machines work and how they decide which function to call under different scenarios. So both AWS Steps and Azure Logic Apps work in a very similar way here. Okay, so far we've been looking at the three clouds and how they implement different technical architectures and so on. Now I want to look at DevOps and how DevOps can be done in the cloud, but it can also be done on premise. So we're still talking about on premise versus the cloud. But DevOps is really a whole paradigm of how you do business, and it's cultural as well as technical. So I want to talk about the whole big picture and then dive into how you do it in the clouds and so on. So bear with me as we go through some of the background. So DevOps is a big cultural change for your organization, typically from the old kind of having a huge monolith piece of code where you would make lots of changes for a long time and then build the whole thing together and then test the whole thing together and then move the whole thing out into production, or maybe do a testing in a staging environment for a few months before you move out to production. And then you find out that actually there's a new requirement and it needs to be in production kind of now, but you can't easily do that because then you've got to change lots of things in the monolith. That's kind of the traditional way of doing code, and it was very inefficient and very slow to get new changes into production, and there were lots of issues around it. Basically, managing a huge monolith of code is so impractical and so difficult. So DevOps is like changing the whole mindset of how you do code, how you deliver functionality, and really it's changing your whole organization. So this DevOps is not just technical, and that's the big thing to get across here. So when we look at DevOps, we look at the CALMs. So the CALMs stand for culture, automation, lean, measurement, and sharing. So what does that mean? So culture, how the company operates and behaves, is going to change considerably if you're really going to move to a DevOps environment. Typically, you're going to go to Scrum, Agile kind of mindsets with sprints. Those sprints are going to be the kind of end result of a roadmap. All your planning at the top level is usually all about looking at the business strategy and how the IT strategy maps onto the business strategy, and looking at the roadmap for the next year or the next 3 years or the next 10 years. You're going to come up with a roadmap and then break that down into sprints pretty much. That is the whole culture change to the environment that you're going to be talking about if you're going to DevOps. So a lot of that is about people and not process and not tools. It's more about people. So first of all, you've got to change people's mindsets. You've got to train them in how to think in that way. You've got to train them in how to look at the big picture and how the business strategy maps to the IT strategy. You've got to train them in looking at roadmaps over a long term and a short term. You've got to train them in looking at things as sprints, where you can get a little bit of functionality done in each sprint, and how those sprints map together for each different group. So there might be 10 different software groups in the company, and each of those software groups have teams within it, and each one of those teams is working on a different piece of the work for each sprint. And how does that all meld together, and how does that all come together at testing time and deploy time to the staging and the production environments? How does the testing work around that? It's a complete culture shift. So it's people as well as process as well as tools. It's complete culture shift. So the other thing about DevOps is it's all about automation. So the better you can automate everything, the closer you are to a true DevOps mentality in the organization. So typically at the code level, that's talking about not just automating the code and the deployment of code, so the build of code and the deployment of code, the checking in of code, you know, typically using something like Git or GitHub. When you check in the code, maybe the code goes through like a testing process, either like a SAS process, which is like it's kind of like an analysis of the code to find security problems and coding quality issues and that kind of thing. Something like lint, that there's various types of lint plugins that you can plug into GitHub and so on. So not just that, and not just that when you build the code, you know, does it check that the unit tests compile and work and run correctly and so on. Having gates between all of those and checking that if the unit tests don't succeed, the code does not move forward into the staging environment, for example. And if the integration tests don't succeed, the code does not go through to the production environment, for example. Maybe there's security tests and penetration tests that you have to do before it goes into the production environment, that kind of thing. But not just all of that, but even coding the infrastructure so that infrastructure is also automated. So rather than set up a virtual machine or even a physical machine, rather than set it up and deploy code to it, deploy the operating system to it, configure the packaging on it, configure ports on it, and so on. Instead of doing all of that, you automate infrastructure. So you write infrastructure as code. So you write a YAML file, for example, that says, I want a virtual machine, and that virtual machine should have Windows on it, this version of Windows. It should have this port open. It should be running IIS. It should have this virtual directory, and it should be configured with these access permissions. Writing it all as a YAML file as infrastructure as code so that it can be automatically created. The infrastructure can be automatically created, and the infrastructure can be kept in step with the code for the actual the applications, so that those are all automated together, so that when you roll out a new version of an application, you also roll out a new version of the infrastructure. You roll forward the infrastructure. So for example, in the previous release of code, maybe you didn't need port 22 open on this particular virtual machine, but the new version of the code needs that port open on that port 22 on that virtual machine. So that change is in that infrastructure as code, goes with the actual code changes. They're both checked in together. They're both compiled and checked together. The unit test, or the integration test, sorry, will check that that port is open at that point, and so on. Also automating via configuration files. So for example, you might have a virtual machine in a dev environment that's different to a staging environment, that's different to a prod environment. In prod, you might want fewer ports open than in dev, for example. So you'd have the development machines might have you know, some ports open for RDP, remote desktop, but the ones that in prod, you don't want those ports open. You want to really nail down the security in production. And also you want to automate as much as you can as far as scripts and so on are concerned. Now scripts can be doing things like updating, you know, packages, updating the operating system. They can be copying files, all that kind of thing. Run books that can help with maintenance of the system, can respond to events in the system. For example, a script could increase the size of the storage space if the database gets beyond a certain size, something like that. So they can all be built in as well. So automation is key to DevOps, and it's very, very important. Lean is the next concept. How much is reduced down to a minimum, and how can you reduce the repetition in the system? So there's a concept called dry, don't repeat yourself. You try to make everything as modular as you can and reusable as you can, packaged as you can, reduce everything down to only saying it once for anything, so that you don't have to keep repeating it. You don't have the same code duplicated many times. There are some tools that you can use to analyze your code to find out if there's repetition, if the same code appears in many cases, and so on. So aim to be lean. Also, just-in-time operations. So the idea of doing something once and only doing it on time. For example, like I said, with the two different versions of code, one version of code did not need a port open. The next version of code does need the port open. So don't have the port open until it's actually needed, that kind of thing. Measurement is key to DevOps. The more you measure something, the more you can manage something. Measure as much as you can afford to do. So in DevOps, typically things that you want to measure are how many lines of code are being produced per sprint. That helps you to manage future development so that you can predict how long it's going to take to do similar pieces of work later on. Measure downtime of systems, SLAs, work out, for example, if you've got something in the cloud, if Amazon AWS goes down for a couple of days, you need to measure that so that you can claim that money back that AWS agrees to in its SLAs, for example. If your systems go down on premise, you want to measure that so that you know that you're improving downtime, you're reducing downtime over time, and you can work towards a better SLA internally so that your system's up 99.99% of the time or something like that. Also monitor the number of errors, the number of bugs found, that kind of thing, so that you can see improvement over time. You can help your programmers and your designers to work out ways of reducing the number of errors, reducing the number of bugs found by improving processes. Continual improvement, continual process improvement is key to DevOps, and measuring that is key to that, so that people can see the visibility is there, they can see how much it's improved. Another side of measurement is having dashboards so that top executives or medium level executives can see at a glance a traffic light scenario. So they have a red traffic light if the systems are down and a green traffic light if the systems are all operating normally, that kind of thing. Having the analytics behind that, having the measurements behind that, so that management knows what's going on and has that visibility, that helps a lot. Things like how many customers are coming into your systems should be measured, and where they drop off on your system. So if you use something like Google Analytics, you have a sales funnel which basically measures how many customers get to different stages in a shopping cart, for example. You can see where the shopping cart drops off. So for example, if a lot of customers get to the point where they've put something in the shopping cart but they don't actually buy, that can be a clue where you might have a problem in the system. For example, on that particular page, maybe there's a bug and they put something in the shopping cart but they can't actually check out, or they can't put their credit card information in there or something like that. So you can watch the sales funnel and see the page that they drop out at and see if there's a problem which is costing your company money because people are not actually fulfilling their shopping cart and going through and actually buying. So the more you measure stuff like that, the more visibility you have into those stages in the shopping cart or the website process, the better you can help the company to make more money and solve problems and so on. And that's key to DevOps. Sharing is key to DevOps too. How much information can be shared between teams, how much code can be shared between teams in packages, for example. You can make NuGet packages or NPM packages, that can be shared between teams, so that there's common functionality that only has to be developed once and can be reused. That can reduce coding time significantly, and it can also increase consistency significantly. It also means if a bug is found, it only has to be changed in one place, and it will be fixed for everybody, and so on. And how much business processes can be shared. Again, it's a mentality, a culture change of how much you can share those business processes and so on. An idea of how DevOps evolution is happening in IT and software. So we're moving from the left-hand side towards the right-hand side. So ideally, if you've got an ideal DevOps company, you're all on the right hand side. So rather than doing manual provisioning of servers and installing operating system software and updating packages manually and so on, you're going to use infrastructure as code. So infrastructure as code might be Terraform, or it might be CloudFormation templates in AWS, or it might be Azure resource management templates in Azure, or so on. And infrastructure as code typically is YAML files or JSON files that have key value pairs or parameter values and so on, and they can be reused. The key is that you can reuse these templates, and so you don't have to keep reinventing the wheel, and you know that you will have, you know, a web server with the right ports open and the right permissions and the right access controls and so on, by reusing the same infrastructure as code templates, so that it will reduce the amount of work needed to set up a new server compared to manual provisioning and so on. The infrastructure as code, as I said, can be managed as code just like your other code, like your application code, and kept in step. There's so many benefits to using infrastructure as code. We talked about configuration management for the different environments. You might have dev, stage, and prod, and you might want different configurations for the different environments and so on. And how you might use configuration files for the app config, for the application itself. So the application itself might have different parameters depending on the different environments and so on. Manual builds in the old days were troublesome and inconsistent and so on. Continuous integration means that when you check in your code, it's automatically built, it's automatically running the unit tests. If it passes the unit test, there might be a gate that says if it passes all of the unit tests, then it can go into the next environment, which might be staging. Then your build automatically kicks off that continuous integration. Then deployment, so that might be continuous delivery into the different environments. So literally you could check in your code right now with your latest change, and assuming the unit tests work, assuming the integration tests work, assuming the security tests pass, it could go straight the way through from dev to stage to prod and be live within minutes. And that's the idea of continuous delivery. Compare that to the old days when you had the huge monolith and you had to do all these things manually, and how long it might take to get that change into production. And now the change can be in production in minutes. We talked about testing and how that can be automated in the pipeline. So DevOps typically has a pipeline, and the pipeline goes from dev to stage to production, and has testing at each stage to make sure that nothing gets past the gates that doesn't meet certain criteria, so fewer bugs get into production. DBA work. So in the past, writing DDL and DML for changes to the database, they might be out of step with the source code for the applications and so on. Nowadays we have schema migrations, which are automated changes to the database that are in step typically with the code changes, so that when you release a new version of the code, you also release a new version of the database. You migrate forward, you roll forward to that new version of the database, just similarly to the infrastructure as code rolls forward to the new version of the infrastructure. The schema migrations migrate to the new version of the database that goes with the latest code as well, that goes with the latest release of the code. And also specs. In the past, developers are notorious for not liking to write documentation around their code. Often designers don't know the detail of the technical details of the specs and so on. So often manual specs were out of date, were bad, and so on. Nowadays, automated specs are possible using DevOps tools, so that you can get automated documentation for your code, for your configuration, for your infrastructure, and so on. And that makes everything much more reliable and consistent and up to date, and so on. That work better with pictorial representations. This is a typical software development life cycle, showing that you do the design and the planning up front. You write the code. That can be automatically, when you check in, it can be automatically built and tested. And if the testing works, it can go to release and then to deploy and then into production, which can be, operated and monitored and so on. And all of these stages, if anything doesn't work, it can go back a stage. So for example, if the code is checked in and it's tested and the tests fail, then the code does not get released, it goes back and the coder has to make changes to the code so that the tests succeed. If the code fails for other reasons, the feedback can be sent back to the designer, to the planner, and so on. If the release goes okay, it can automatically deploy into the production environment, and in operating, you're going to be monitoring automatically as well and running the system automatically. So for example, some automation that you might have for operating a system, you might monitor to see if the virtual machines go over 80% memory or high CPU, and if they do, maybe it runs a script, or maybe it makes a change to the load balancer to say, let's have 3 virtual machines instead of 2 because we've got high load, or because we're using a lot of memory on the other virtual machines, and scale in and scale out and so on. Obviously in the cloud this is a lot simpler, as we've talked about earlier, than it is on premise, but having these automated monitoring and operations tools available in DevOps makes things a lot easier. For example, you might have run books or playbooks that run in particular scenarios. If you detect like a heartbeat going down or a health check isn't working. So a health check is something that you use in production typically to find out if a piece of code is not working as it should. For example, an API might have a /health URL that you can call, and when you call that URL, it either returns a 200, which means okay, or a 400, which means something's wrong, or a 400 and something that something's wrong. And then within that, it might return a piece of JSON, and the piece of JSON tells you which dependencies are working correctly and which dependencies are not working correctly. So it might check the database that API depends on, or it might check an external API that this API calls. And if there's anything down, if there's anything not working, it will return a 400 code, for example. And that can be detected by your monitoring software automatically to automatically make changes to your environment in that circumstance. So it might use an alternate API URL for the external API if it detects that the external API is down, for example. Or it might change the load balancer configuration according to some rule that you have an alert based on. Or it might just send an email to an SRE. An SRE is a systems reliability engineer, somebody who responds to emails that come from the system or alerts that come from the system when something is wrong. They they know which script to run, or they know what to do in that circumstance, who to inform, that kind of thing. So the more you can automate this stuff, the more the system can be self-healing, and that's what you really want, so that you don't have to rely on human interaction, which is typically slower than automated reaction. So that's, DevOps trying to build as much automation into this whole software development life cycle as possible. So we've kind of talked about a lot of this already, but DevOps in the cloud is very similar to DevOps on site. We've talked about both. You do planning, you create the code, you build, you test, you verify. So you do unit tests, and you do integration tests and system tests and security tests. You package as much as possible so that you can reuse common code. If you can publish one build of your code, you might be able to just publish that to the different environments, to staging, for testing, and then the same exact package can go to production to ensure there's consistency between the version that was tested in stage and the version that's running in prod. Operations is all about releasing and deploying to the different environments and configuring your system out there in the cloud, monitoring your system out there in the cloud, hopefully doing that in an automated fashion with self-healing and self-monitoring, and like a feedback loop, that if there's something wrong, what should be done in that situation. Is there a run book? Is there a set of scripts that should be run in that scenario, and so on? Let's have an automated system as much as possible to keep that system running in production operations. So DevOps is kind of a combination of these two. It's collaboration between development and operations. And nowadays, coders are often expected to know dev and ops. Coders who write the code don't just write the code, but they write the code to deploy, to configure, and to monitor the system as well. So there's an expansion of the requirements of coders, there's an expansion of their skill sets required, and so on. They need to be able to write infrastructure as code, which we talked about before, which could be Terraform or could be CloudFormation templates or Azure Resource templates. Typically, it's a YAML or JSON file with a lot of parameters in it. So coders who are used to writing Java or JavaScript or what have you, C#, they now need to know how to write these YAML files and put the right parameters in. They have to know a bit about the infrastructure, which ports need to be open, how to configure a load balancer, that kind of thing. So you typically have smaller teams with wider skill sets. So a DevOps team combines the best practices that we've talked about, the culture, the mindset, the software tools, and so on. And the idea is that at the end of the day, we deliver high quality products because they've been tested in various ways before they get into production. We deliver them faster because, assuming that all the tests work, they can get into production very, very quickly, and also more reliably, so that it's less likely that you're going to find bugs in production because of all of this. And these loops show you, the DevOps way of doing things, the kind of methodology, and we've kind of talked through some of that already, and there's a couple more slides about that later. Show you that monitoring is key in DevOps. The more you have observability, the more things that you measure, the more factors that you measure in the system, the more you can monitor those factors. So for example, if you're measuring things like memory and CPU and disk I/O, then you can monitor those by graphing them and displaying them to management or to the developers. And then you can also create alerts which trigger based on different levels of those, and so on, and do something and self-heal or do something in the system. Also, once you've got all that data, you can do analysis and machine learning based on all of that data. So you can say, based on current trends in this system, the likelihood is that we're going to need more virtual machines over this weekend because whenever marketing does a particular campaign, we get a lot more traffic. So, let's have some virtual machines set up already in anticipation of that marketing campaign, because we know we're going to need some more virtual machines that weekend, that kind of thing. You can look at trends, you can make decisions, you can do machine learning so that you can make assumptions based on past history and past behavior in the system, and so on. This is again for you visual people, really just saying what I've already said in words. When you commit code in the DevOps pipeline, you're going to commit into something like GitHub or something like that. It will do the build, typically using something like Jenkins or Octopus or Azure pipelines and so on. It will do the build, and if the build succeeds, then it will go through to unit testing and do unit testing on the code. If anything fails at that point, the code goes back to the coder, and they have to make changes to the code because of a failed test or failed build. But if the unit tests all succeed, then that code may be merged into a kind of trunk, which may then be placed into integration testing. Integration testing succeeds, then it might go through into staging. If the integration tests fail, again, that goes back to the coder. If we get through the integration testing and go to staging, there might be some regression testing, there might be some security testing, pen testing, DAST testing. DAST is kind of dynamic website external testing to make sure, it's a bit like penetration testing really. And again, if that fails, it goes back. But if it all succeeds, then it might be deployed into production. So this is just a visual representation of some of the stuff we've been talking about. And I've got a couple more visual slides for you visual learners. So this is DevSecOps, which is DevOps with security built in. And it kind of goes hand in hand, but I just want to explicitly say some of the security stuff. So when you're planning for DevOps, don't forget to plan for the sec part of DevSecOps, security side. So look at your threat landscape, look at the things that can go wrong, look at the kind of ways that you could get a breach, and work on, how you can build that into your DevOps pipeline. One thing you can do is when you check in your code, you can have SAST tools. They can be plugins, or they can be pre-commit hooks that do checks to make sure that you've got no code quality issues or security issues in your code. For example, if you've hard coded in the password for the database by accident in Dev, you've checked it in, something like that, then these SAST tools will pick that up typically. Before you put it into the wrong environments. Then in build, again, you can have SAST tools doing the same kind of checks. At that point, they can also do component analysis. For example, if you're using a NuGet package that has known vulnerabilities, it will let you know before you put it into another environment, and so on. In the testing part, in your unit tests, for example, you might want to check for security vulnerabilities. You might want to check the authentication works in your integration tests. You might want to check for SQL injection protection in your integration tests. DAST is more like a penetration test for a website and so on. You want to check that there's no vulnerabilities in your landscape, if you like, in your external landscape. So no ports open that should not be, and that kind of thing. Then in release, when you're actually releasing the code, you want to make sure that there's access controls and configuration management to make sure that anything in dev is configured differently to in production. You don't want the production database to have dev credentials and vice versa, and so on. In deploy, this would be penetration testing, which is kind of just checking that there's the hardened outside of your system is intact, and that even if someone's really trying to get in, your system can handle that, especially your infrastructure can handle that. Your load balancer doesn't get overwhelmed if there's just so many calls coming in because of denial of service attack, that kind of thing. Also chaos engineering. So you might have heard of the chaos monkey that Netflix employs at this point. So before they deploy, they basically let lots of things go wrong in their staging system and make sure that the system self-recovers or self-heals from those issues. And if it doesn't, then they don't deploy it. So that's chaos engineering. It's actually making things go wrong, putting problems into the system in something like the staging environment to make sure that your system self-heals from those correctly and does what it should in those scenarios. So this might be, for example, in the cloud, this might be if one availability zone goes down, does the system still respond to customers? If one region goes down, does it switch over to another region? Does the database fail over correctly? That kind of thing. That's chaos engineering. So in production, you don't want that to fail. So in staging, you actually mimic the database going down, or you mimic the region going down, or the availability zone going down, and see if the system responds to it the way you expect it to. Monitoring is all about, collecting logs, collecting data, finding out what's happening in the system. Like I said, the more you measure, the more you can manage. And especially from a security perspective, the more you measure what's happening in your system, if files are changed, if access is happening that shouldn't be happening, audit trails, logging, all that kind of thing. Collect as much as you can, and then either report on it or alert on it, so that you can make good decisions and you can manage the system correctly. And then you can respond in point 8 to block attacks, maybe using a WAF or using intrusion prevention systems to block attacks and so on. And then you can roll back if something goes wrong. So if you actually did a deployment that actually worked for a while, but then suddenly was doing something really crazy in production, you could always roll back to a previous version. It could self-heal. It could do that automatically, and so on. So that's DevSecOps, and how that's a slightly different slant on DevOps because it builds in the security side. I just wanted to go into detail of how one particular cloud provider does DevOps so that you can see how DevOps is done in the cloud. So I think Azure probably does DevOps the best out of all 3 cloud providers. Azure DevOps is kind of a separate system within Azure, and it handles the whole of the DevOps processes, really. So Azure boards are used for planning. You can create features that you want in your roadmap, and those features can be broken down into sub-features, and the sub-features can be broken down into what's called PBIs, which are really like stories in something like Jira, pieces of work, discrete pieces of work, and those can be broken down into tasks as well. And then you can attach testing to that. You can basically manage any piece of work in your sprint. In your sprints, you can have backlogs, you can have refinement of those backlogs and deciding which of those pieces of work you're going to do in each sprint, and so on. So that's all managed using Azure boards. Repos are very similar to Git or GitHub. They're used for storing code or artifacts, and very much like Git or GitHub. And you have branches and so on. You have pull requests where when you've made a change to some code, you can check the code in, and a pull request is where somebody else will review that code and make sure it's okay and approve it before it goes into the build. And then you have the build run by the pipelines, and the pipelines are typically used for building the code, packaging the code, testing the code, and deploying the code. You can also use pipelines for some management and some of the operations management of your system as well. Azure test plans are used for creating plans for testing of the code. Azure artifacts are, it's really like JFrog Artifactory, something like that, Nexus, where you can create builds and make packages, and those packages can be shared by other code, or they can be deployed into different environments. It's nice to know when you're deploying to the different environments that you've got the exact same version that was already tested in staging, and now you're going to just move it into production because it's fully tested. If you know exactly the same package is moving into production, that's how Azure Artifacts kind of works. Azure Monitor, we've talked about that before. Azure Monitor is not strictly part of the DevOps system, but it kind of works hand in hand with it. Azure Monitor is used for monitoring all of the resources you have in Azure, from virtual machines to load balancers to serverless Azure functions or app services, and everything really. And you can monitor the performance in terms of memory, disk, CPU, etc. You can provide alerts when you get to certain thresholds, and those alerts can send emails or text messages to different groups and so on. Azure App Insights is for looking deep inside your code to find problems like exceptions and errors, and locating the exact line of code potentially that's causing a problem, and so on. So all of that is provided as part of DevOps within Azure. AWS has CI/CD tools. They're called AWS Code Pipeline, which is very much like Azure Pipeline, software releases and workflows and gates and so on. Very much like Jenkins, very much like Octopus and so on. AWS Code Build, which is very much like Git or GitHub, where you can check in your code, you can have branches, you can build, you can test, you can do unit tests and so on. Deploy automation is just like Azure Deploy, where you can code deploy, you can deploy your code into the different environments, into dev and prod and staging and so on. And then CodeStar kind of manages all of this together and manages the whole CI/CD process in AWS. So AWS Code Artifact is similar to Azure Artifact, which both of these are similar to Artifactory, JFrog Artifactory or Nexus and so on. Both support Maven, NuGet and NPM packaging. They support Python in different ways and so on. So they're very similar. So we've talked a lot about Azure Monitor and Azure App Insights, and AWS CloudWatch is very similar to Azure Monitor. AWS X-Ray is very similar to Azure App Insights. I personally prefer the Azure tools in this area, but they're very similar. The part of DevOps is managing the system once the code is out there, kind of thing. So automating a lot of operations work is a big part of that. So Azure has Azure Automation and AWS has AWS Systems Manager. And the idea of both of these really is to automate as many processes as possible, to run scripts, to run runbooks, to provide scheduled updates and package updates and operating system updates, that kind of thing. They all do all of that kind of thing. Asset management, so knowing which assets are out there and which ones are in which state. Often these tools ensure that if one virtual machine is down, the other one is still running, so that if you're doing like an upgrade of an operating system on one of the virtual machines in a load balancing configuration, it will only do one at a time to make sure one still stays up, that kind of thing. So in this case, these are pretty similar systems. I think the Azure Automation is a little bit better than the AWS Systems Manager, but they provide similar kind of functionality. Scheduling, secret management, runbooks, scripts, change management, and so on. So for compliance in the two different clouds, in Azure, you've got Azure Policy. In AWS, you have a few different things. Really, AWS Config is the closest to Azure Policy. The idea of those two is really to make sure that the configuration of your virtual machines or your load balancers or what have you conforms with the policy, the company policy. So for example, you might say, port 22 should never be open on any virtual machine, and Azure Policy would report if that port was open, and so would AWS Config. Any issues found, they report on in slightly different ways, but you would get a compliance report to indicate where there are exceptions, where there are things that are not compliant, and so on. AWS also has things like Audit Manager and guardrails. Guardrails kind of protects you from compliance problems. It basically doesn't allow people to do certain things, and it assumes or it requires certain things to be done and so on. But pretty much this is the offering in the two clouds. For security, Azure Sentinel is second to none. It is a fully security information and event management compliance tool. AWS does not have the equivalent. Azure Sentinel is also a security orchestration, automation, and response tool, but AWS does not have that. The thing with AWS is it splits a lot of the requirements of these tools into different parts of it. So AWS has a number of different tools that do these things. So Guard Duty is an intrusion detection system, intrusion prevention system. WAF is also intrusion prevention system. Security Hub Inspector. The inspector basically looks around the system to find any problems with the security setup and so on. Security Hub is where you put your settings in that you kind of require for security purposes. CloudTrail is an audit trail, really. You cannot change it. No one can change it so that it can be used for audit purposes. CloudWatch is more like Azure Monitor. It monitors things in the environment, monitors your resources, things like CPU usage, disk I/O. You can also import your logs into CloudWatch and so on. Azure Sentinel pretty much does everything. It includes things like threat hunting, compliance, alerts, reporting, dashboard visualizations, and so on. There's also a tool called Micro Focus ArcSight, which is a good SIEM, which you can use that on AWS or Azure to provide full SIEM and SOAR. Again, for your visual learners, DevOps is trying to move from not automated manual testing through to automated testing at the top of the screen here. So that means unit tests are usually the first step because they can be automated. Then integration tests, which check that different parts of the system are talking to each other correctly. And then end-to-end testing, which tests, right from the front end when you enter something and you press the submit button, does that get all the way through to the database and back out and get sent back to the user interface, the front end, and so on. And can you automate all of these kind of tests? And then there's exploratory testing as well, which is exploring different ideas, exploring different deployments. So you might have green-blue deployments so that the current version of your code might stay green in production, but then you might run a blue version of your code 80-20% or something like that, so that 20% of users on the front end will see a different front end and see if that works better than the existing version of the code and that kind of thing. So can you automate that as well, and can you deploy that automatically and so on? Again, this is just a visual interpretation of some of the stuff I've already spoken about. So you write your code into your code branch in your local machine. You do some testing in there, usually using unit tests and so on. A pull request is where you ask someone to check your code and do like a QA, a check on the code changes that you've made. That's another kind of test. That's actually like a manual test. And then you merge it into the main branch in development, and there'll be tests done there. That could be a SAST plugin that checks for code quality issues like SonarLint. Could be just rerunning the unit tests. And then, in the main branch, you could have integration tests, you could have DAST tests, penetration tests, and so on in a staging environment before you get to production, and so on. And then that's all automated. And then the final gate would be to get into production. And that's when all of the tests have worked and all of the approvals are approved, and then it gets into production. Earlier in this series, we looked at Azure versus AWS versus GCP in terms of a lot of the offerings that they provide. One area we didn't touch on was some of the data stuff, so I just wanted to go through some of that before we end this session. So stream analytics and data streaming is a key area of data handling nowadays in the cloud. The idea is to get data in as fast as possible, as real time as possible. So Azure does that via stream analytics. AWS does that via Kinesis data streams. And data analytics can sit behind Kinesis data streams to do some analytics based on the data streams. You've also got Kinesis Firehose, which basically streams in data really fast, but does some calculations or some manipulation on the way in, and tends to work not quite in real time, tends to be like about a 60-second delay, but is often used for dumping data fast into data lakes or into data warehouses. So GCP pretty much uses Kafka for this purpose, and of course you can use Kafka in Azure and AWS as well. In this presentation is data warehouses. So AWS has its own answer to data warehousing, which is called Redshift. Azure has two, one of which is called Cosmos, one of which is called Synapse Analytics. It depends what you want to do, which one of those you're going to use. Synapse Analytics is probably a more typical data warehouse with more typical data analytics capabilities. Cosmos has a number of kind of layers that you can see Cosmos through, if you like. One is a document store layer, which is more like a MongoDB interface to Cosmos. There's a graph layer, which makes Cosmos look like a graph database, which I think is called Griffin, I think. And there's also a key value store option and a wide column store. So depending on what you actually want from the database, Cosmos is pretty flexible and can do different kind of modeling according to what you want. Synapse is more of a straightforward data warehouse with straightforward analytics, a bit more like Redshift. So Redshift also comes with some business intelligence tools. It now comes with Spectrum, which is really a way of looking at your data lake as though your data lake was within Redshift as a table. So that's a really useful new addition to Redshift, and it makes it into a data lake house, which basically means a data warehouse that can access the data lake. So that's a new thing for Redshift. So GCP has, so Google Cloud has BigQuery, which is a data warehouse service with append-only tables. So, there are some limitations on that, but it is a large data warehouse dealing with columnar data, if you like. So all three of these offer columnar data capabilities. We're going to use that to explain how you would create a kind of software roadmap, how you would turn that into sprints, and also how you would incorporate into that things like restructuring your technical architecture for a migration from on-premise into the cloud. So this case study kind of handles a lot of things in one case study. So I think it's really useful. So just to simplify the case study a little bit, because it's already quite complex, we're going to make some assumptions about our case study. Our case study is Bicycles, which is a fictitious bicycle shop company which sells bicycles online. So we're going to make some assumptions. There's no multi-tenancy issues. So what that means, a multi-tenancy issue is, for example, if you have a software as a service system in the cloud, for example, like Microsoft 365 or Office 365 as it used to be known. For example, Microsoft has many tenants in Office 365 or Microsoft 365. So many tenants would be, for example, Coca-Cola uses Office 365, and so does Walmart, and so does a bank. Okay. So they're all tenants, they're all customers, and you want to ensure that one tenant cannot see each other's data. So you want to make sure that the Word documents that are owned by Coca-Cola are not seen by Walmart or seen by the bank, and so on. So those are multi-tenancy issues, making sure that a tenant cannot see each other's data and that kind of thing, and siloing a tenant so that their data is completely separate to the other tenant, and so on. So we're not going to have any of those issues in this case study, so that we make it a little bit simpler, because it's already quite complex as it is. So we are going to assume, though, that Contoso Bicycles has multiple views and stakeholder types. So when you're looking at a business and technical strategy, one of the things you're going to look at first is, are there multiple stakeholders? Okay, so in this case, this Contoso Bicycles online store has customers, it has suppliers, people that make the bikes and supply the bikes, it has employees, it has admins who admin the site, who look after the site, so they might be SREs, system reliability engineers, and it has IT support, so that might be kind of SREs level 2 or 3. It might be people who have phone calls from customers and so on and so on. So the main purpose of this site in this case study is e-commerce, so e-tailing, retailing online, selling these bikes to customers. That's the main purpose. We want it to have a relatively simple architecture. Now that is, of course, a tricky concept, but that's what we're going to aim for. We're going to assume that demand goes up and down a great deal. For example, when Contoso Bicycles puts an advert on their national TV, suddenly everybody wants to buy a bike, and we get lots of load and lots of demand. So scalability is going to be really important, so that we can meet that demand and we can handle it. But there's no high security or compliance requirements here apart from credit card processing. So we don't have to comply with HIPAA or SOX or anything like that for the purposes of this case study. And security requirements are pretty limited. There's not much danger here. We're not a bank. We're not a government institution, and so on. For each one of those, you do some planning. You get ready, you adopt, and then in the adopt phase, you have a number of iterations, which is the migration effort itself. So iterations pretty much are similar to sprints. For each iteration, you're going to assess the workload, you're going to deploy the workload, and you're going to release the workload. So this is kind of how they do their migration efforts in iterations. Roadmap being a big picture roadmap of steps, really, from current state to future state. And this roadmap has to be in the business strategy, the IT strategy have to be in sync with each other. So now we're looking at the kind of baby steps, the steps below that. So what actually becomes sprints pretty much, okay? So the first part of this is going to be move the monolith. So lift and shift what we've currently got on site at Contoso Bicycles' own data center and move that into the cloud. So step one of all of that is going to be talking about how we're going to do it and planning it, kind of thing. So step one is going to include communicating the plan to move into the cloud, deciding which cloud we're going to use. In this case, it's going to be Azure. Training the people who are actually going to do the work. So training the middle tier personnel in how to design and build microservices, how to use Kubernetes as a tool to build microservices. That might be one of the steps, for example. To train the front end tier in the technologies that you're going to use at the front end. In this case, we're going to use Blazor. Blazor is very much like Razor in the old days for JavaScript, and Blazor uses C# instead of JavaScript, but basically it's a front-end technology that you can use to quickly and easily design the front end of a system. We're going to train everybody in Azure and cloud concepts, so that everybody, including business management as well as techies, know what Azure is, what cloud concepts are, how all of these pieces fit together. So that's part of the planning stage. And then we're going to plan for these dev, stage, and prod environments. We're going to work out, which subscriptions and which tenants and which Azure Active Directory environments we need, that kind of thing. This is all kind of planning stage stuff, okay? And we're going to talk about how we're going to move that into front end, middle tier, and back end on Azure. So on the right hand side here, you can see the web tier, the business tier, and the data tier with a DMZ at the front of it, and so on. So we're going to start writing some high level technical tiers, if you like, of what the technical infrastructure is going to look like, what the technical architecture is going to look like. So that's step one. Step two, we're going to do the simplest low-hanging fruit of the migration, okay? So the stuff that's really easy is to take existing SQL servers that are in the on-premise environment and move them into the cloud using Azure SQL Server. So that's like an Azure managed instance SQL Server. So basically there's no code changes involved in that. The SQL Server can move and lift and shift exactly as it is. Without any code changes. Azure managed instances make managing that SQL Server even easier than it is on premise, because Azure will handle things like scalability, backups and recovery, and failover, and all that kind of stuff. So that's a really low-hanging fruit. That's really easy. Step three will be all about deploying the existing middle tier monolith to the business tier in Azure with a load balancer in front of it. So literally lifting and shifting all of the middle tier as it currently stands on premise and moving it over into Azure with a load balancer in front of it. Now, obviously, eventually we don't want it to be a monolith, but that's how we're going to do it first of all. Step four is doing the same thing for the front end. So taking the front end exactly as it is and putting it in the web tier on Azure with a load balancer in front of it. Literally the monolith as it is, exactly the code as it is. Step five will be implementing load balancing, failover, some DevOps stuff, some security into the architecture, and then using some infrastructure as code to build the architecture. So to create the load balancers, to create the virtual machines using infrastructure as code template, and making sure they're reusable and making sure they're dry, don't repeat yourself, and so on. Making sure that code is stored in GitHub or in in some sort of code repository in Azure DevOps in the repos and so on, just to make sure that the infrastructure as code is kept in sync with the code for the development. Okay, so that's the first 5 steps. That's the first 5 baby steps. So basically, those 5 steps have got you to the point where the whole monolith exists in Azure. Okay, so now we're going to deal with the more detailed steps that are required for the middle tier. So once you've got the kind of monolith middle tier in Azure, there are more steps that you have to take, obviously. So one of those steps might be to convert the whole of the middle tier monolith to .NET Core if it's not already in .NET Core, to make it all built using dependency injections so that you can do good unit testing and so on, and you can make everything loosely coupled. You might have to decide what you're going to do with the middle tier in terms of, are you going to make it into Blazor server code, or are you going to just use C# .NET Core code? You might convert the middleware, so the HTTP modules and handlers, to the .NET Core middleware. You might implement authentication and authorization using something like OAuth or JWT, so that for authentication purposes, the person has to prove they are who they say they are via a username and password, or so via something they know, something they are, or something they have. So something they have might be an authentication app. Microsoft has an authenticator app, and they have to type in a code, that kind of thing. So authentication is that part, proving that you are who you say you are, proving that you've got the password or you've got the authenticator app, and so on. Authorization is, once you prove who you are, what are you authorized to access? Now, what you're authorized to access might be, you might have access to this API, but not to that API. You might have access to this API endpoint with a GET, but not to update it, so you can't do a post or a put or a delete, for example. So all of that has to be implemented using something like OAuth or JWT. So they're different ways of implementing those things. You maintain your external API contract as if possible. So even on-premise, Contoso bicycles probably had an API contract. So it had /bike, it had /order, /shopping cart, I don't know, whatever. And those were the API kind of contracts. And you could do a get and a post and a put and a delete on each of those. Try to maintain the external API as much as you can, but use a V1 or a V2 or a V3 to indicate which version of the API you're on. So it's very similar, but it's on a different version. And that will make it easier for the front end to change to match the new version of the code in the middle tier. And also external users of your API can use it more easily as well, if there are any. So the next step in this middle tier would be making sure that any files that are saved or used use Azure storage rather than just the native file system as it used on-premise. So that may be changing the file storage code to use, Azure blobs or Azure file storage, and so on. You might also implement an API gateway or a load balancer so that you can have your scaling, your auto scaling up and out depending on which kind of scaling you want, and so on. And the other key part of changing your middle tier in this way is to include unit tests so that you can always check that your middle tier works when you check it in, when you make changes. Your unit tests have to pass before it can get into the next environment, like into staging, for example. So that's the first set of steps. Now, the next set of steps will be to identify some key microservices. And so one microservice might be order, one microservice might be bike, one microservice might be account, and so on. And a service typically will own a particular business entity, a small piece of data. And that microservice will allow get, put, post, patch, delete, anything like that on that particular business entity only. So that particular microservice owns all changes to that business entity. All changes to that business entity have to go through that microservice. So what we'll do in step 5 here is create one microservice, a proof of concept of microservices in this environment. Now that microservice might be run in a Docker container on Kubernetes, it might be run as an Azure function or what have you, depending on how you're architecting your system. But you're going to include some testing, some unit testing, some login, authentication, authorization, all of that for that microservice will be in that particular microservice code. And then you're going to coordinate for that particular microservice. This is just one microservice, a proof of concept microservice. Coordinate with the front end for end-to-end testing of that particular microservice. So the front end will have to make some changes at the front end to call that microservice. And then you're going to publish that proposed new microservice or API and publish that plan for how that works. And what you're going to do with that is you're going to use that whole microservice as a kind of sexy tool to say to everybody else in the company, look, this works. Microservices work. These great coders in this particular team, normally it's a Scrum team, maybe a Scrum team full of the best programmers in the company, they created this microservice, it works, and we can run it from the front end, we can call it from the front end, this works, so now we can do it to all the other microservices. And the next step is to identify other microservices that you can do the same thing with. And you're going to go through gradually making more and more microservices work in this way, with REST APIs to them, and coordinating with the front end team for end-to-end testing and so on, and including unit tests. By the way, once you've done your proof of concept microservice, you can use that as a kind of template for all your other microservices. As much as possible, do a dry development, so don't repeat yourself. So anything you can reuse from the concept microservice, reuse that in creating your other microservices. Layer of microservices is created, then you can decide whether you want to do any sort of extra complex orchestration like event grids and queues and service buses and decoupling via queues and things like that. If you want to create any aggregating microservices as well, so microservices that call other microservices to aggregate information and create printing or reporting functionality that goes across many microservices, for example. You might want to use something like Service Fabric and so on. So there's those kind of decisions, but these can come in later steps. So each of these steps you can think of as like a sprint, and this is going to be, you know, sprints way down the end of the middle tier development. So later on, you're going to build full testing of the whole middle tier into the whole CI/CD process. So you've already got unit tests for your actual microservices, and then you're going to add in integration testing to make sure that each microservice integrates with each other microservice properly, and with the front end and with the database and so on. Make sure the integration testing works end to end. And then the last few steps for the middle tier baby steps are decommissioning any existing middle tier infrastructure that you no longer need. So the big monolith probably used a great deal of resources and cost a great deal of money, and now you can get rid of a lot of that, and you can start thinking about maybe you can use reserved instances to save money and stuff like that. So you can create a completely new middle tier infrastructure that is cheaper and scales up and scales out and scales back in and scales back down when needed, and so on. And you can deploy that whole new middle tier with that whole new infrastructure into stage and then into prod according to passing the tests in those two environments. So while all those changes have been happening in the middle tier, the front end tier has also been doing some baby steps. So these steps here are how you would do the front end. So the front end, you would convert the front end code into you're going to use for the front end. So in our case, we've decided Blazor. So each view file that you had on your old environment at Contoso Bicycles, which might have been you know, an old MVC app in ASP.NET and that kind of thing, and the front end might have been you know, Razor JavaScript or something like that. So you convert the view file from Razor JavaScript into C# for Blazor and use Blazor. So as you convert each view file, you'll maintain some unit tests for the new file. Now you might use Selenium for the unit testing for a front end, for example. There's, I think, Cucumber and Gherkin and all those kind of things as well can be used. For each controller in your MVC architecture, for example, you may leave some of that as is with just some changes to Blazor in the middle tier, depending how it used to be done, or you may go to a completely Blazor server backend kind of architecture. And then remember that you want to move to, instead of calling ordinary APIs with ordinary, gets, puts, patch, deletes, and so on, you're going to be starting to call these new microservices as microservices are developed in the middle tier. You might want to group your pages by the microservices that they're attached to, that they use. You may want to host those in a Docker container. You might want a Docker container for order and a Docker container for bike and a Docker container for account, just like you have in the middle tier those microservices names. You want to remove state from microservices calls as much as possible. State can be stored in databases, it can be stored in local storage, it can be stored in like Redis caching, but you don't want to use the state in microservices too much. Microservices need to be as stateless as possible. Your microservices might be in Kubernetes, so you might want to move the front end tier into Kubernetes too. That's up to you, but that's a step that you might want to do at this point. And then you want to add integration testing and unit testing fully into that. And again, like in the middle tier, you want to decommission any of the old infrastructure that you no longer need now that you've got it all working with the new infrastructure that's kind of leaner and more scalable out and scalable back in again, and so on. And then you want to deploy the front end to stage and then to prod according to if it passes all the tests and so on. On the right hand side here, you can see an Azure load balancer with Kubernetes underneath with pods, and each pod has nodes inside it. So that might be a typical front end tier at the end of all of this. As code already, but just want to reiterate that infrastructure as code is typically going to be something like Terraform or AWS CloudFormation templates or Azure Source Management. Google also has Deployment Manager, which is similar. There's also something called TerraGrunt, which can sit on top of Terraform, which is excellent, and I really highly recommend it for big migrations. TerraGrunt really only works with AWS right now, although they're trying to move it to Azure as well. But TerraGrunt, basically, you can tell TerraGrunt what kind of environment you want, how secure you want it, what kind of security you want, whether you want a dev, a prod, a stage environment, and so on. And it will basically generate all the infrastructure as code to deploy your whole environment. It's amazing. So highly recommend that. The whole idea between infrastructure as code is to have versions of your infrastructure in code form that map onto your releases of your code, and basically the templates roll forward so that you roll from the current situation to the new situation depending on what the infrastructure is described as in your YAML files or your JSON files. So for example, before you start, you might have nothing in Azure at all. And if you roll forward, you run all your infrastructure as code, it creates, all your virtual machines, your load balancer, sets up all your ports and so on. And that would be your first version of your infrastructure as code. And then you might roll forward to the next version, which opens a couple of ports open originally, and that to the versions of your application code that they map onto. We talked about all this before, but I'm going to reiterate that. This whole roadmap takes Contoso bicycles from having a monolith on-premise to having a monolith in the cloud, and then going to a microservices environment, which The microservices environment is more optimized for the cloud and using serverless components and using the cloud components for the best purposes of Contoso bicycles, saving money. It's all in a 20-step plan. One step might be the equivalent of one sprint, for example. Remember that the middle tier and the front end tier can be done at the same time in parallel. You can play around with the order of the baby steps as you want to, depending on resources and requirements. But the big thing is that you can save a lot of money on infrastructure, especially on the scaling up and scaling down, because you only pay for the high level of infrastructure when you've got the high demand. You don't pay for it all the time in case you get the high demand. You just pay for it when you have got high demand, and then it scales back down again. It's faster to move new changes to production after this because you're going to use a DevOps pipeline that we talked about DevOps in a lot of detail here. Built-in unit tests and integration tests make success much more likely and reduce the likelihood that you're going to find bugs in production. So that's all I wanted to say about this whole thing and this whole case study and DevOps and moving a monolith to microservices and migration and so on. I hope you found this useful. And I hope this helps you to migrate. And if you have any questions, just let me know. Thank you.